The first class I made the quote-unquote mistake of asking you what you wanted, and then I ended up having to deal with all three fronts. So we're beginning to move in that direction. I was focusing, it took me a lot more than I thought the first two classes to cover, but I preferred going slow in the first two lectures, because more often than not, the kind of things I told you are hard to find, or you just find pieces here and there. While as we go into more formulation of numerical relativity, et cetera, things are more or less robust, and there are plenty of good resources for this. So one good one, just because things get updated, is, for instance, Sebastiano Vernuzzi is a prof in Jena, has lecture notes that he puts available on his website that he wrote in last year, 2021, that are pretty up to date. So I suggest you go there. I'm going to be focusing on different aspects and just making sure I tell you exactly what's the key in each of the topics we're going to discuss next. But I want to discuss the last few things with respect to equations in general, and then we're going to dive in numerical relativity. So the first thing is, let me just say a few more things on the equations. So we've been discussing, by and large, the first order equation of this form. Remember, this is the advection equation. And we know, or we argue, this is the type of equation we want to talk about, because any second order equation we can reduce to first order, though it will depend on some other things I need to say. But let me tell, one of the things we have been noticing or working with is what is an equation with, we had u comma t, the time derivative, equal to often a 1 or a constant times u comma x. This is the simplest possible advection equation, but then we can think of complicating it. And one of the things you could do is just, you can talk to your mathematician friend, and it's always good to have a mathematician friend. They keep you humble. At the same time, they keep you feeling that you're useful, or at least more than they are. This is in relative terms. I have mathematicians friends. At this rate, I'm going to run out of friends at the end of the lectures. But, okay, so let's think of this one. Now replace this equation with that. The only thing we change is this constant. We now shoved in the very same field we're iterating. The archetypical example of this equation, in fact, up to a factor of rating in slightly different ways, Burger's equations. So the key thing is that here, as opposed to in this problem, where we would say at every point, things are propagating at speed lambda, what we have here is at every point, things propagate at whatever value u has. So if we have, let me draw it here. So suppose, now let me just draw it here. Suppose you had u having this shape. So we can come in here and say, okay, u is 0. There's no propagation there. The speed, whatever I might have, stays there. But of course, it's 0. But then when I come in here, well, the speed is some number. It's positive. We know that every time we had a positive there, things are moving to the left. But it's moving at that speed that is small. We go a little bit more to the right, and it's moving at a faster speed. And so then these things begin to develop more like this structure. So it gets steepen and steepen. And this is what you experience in the highway when you're driving and an idiot in front of you stops or brakes very suddenly, and then you pile up. So that's called a shock. You're generating a shock, and we'll discuss a little bit more about that. And then on this side, okay, this piece is moving faster than that piece, and so then you begin to vacate the region, and this distribution gets wider and wider, and that's called a rarefaction fan. These are things that happen or show up in hydrodynamics, and we'll discuss a few more things there. But that's delicate. It will tell us. Remember, a lot of many of the things we have been discussing with respect to what's a particular discretization we use, the assumption of smoothness, that breaks down. If we have such a situation, we have to be careful, because smoothness might go out of the window very quickly, depending on the equation we're dealing with, especially if we're dealing with the equation of this type. But then you go to your mathematician friend and you say, well, what do I do with this equation? Where I have now not the field itself, but the derivative of the field itself. And then he or she will look at you and say, well, good luck, we don't even have a classification for that equation. we don't know, we don't have a name. So you're on your own. Let me give you another example. Suppose we're thinking of second order equations. Well, the analog of that one is this one. The second time derivative equal to the second space derivative of the field. Same thing, you can say, well, let's complicate it a little bit more. Let's put a field there, undifferentiated. Well, your mathematician friend will say, well, now became nonlinear. Same thing here. This was a linear equation. This was nonlinear. This is nonlinear. Same here. It became nonlinear. But your friend will tell you, okay, this is something we call linearly degenerate. So yes, it is nonlinear, but by and large, it's almost as linear as this one. It's not that complicated. These kind of phenomena will not show up generically. This is, and we'll discuss more today, this is the type of equations that Einstein's equations will give you. And so it's bad, but it's not really that bad. And in general relativity, we have the equivalence principle, which will tell us that locally, this is even a 1. So we're in pretty good shape. Now we can go into here where we say, well, the second time derivative is the derivative of the field times the field itself. Okay, this we have, if you want the speed of propagation, is the gradient of the field that is twice differentiated. So it's one fewer derivative than that. This is the analog of that. So this will give rise to shocks and discontinuities. And these kind of things show up often in beyond GR theories. And in fact, the kind of theories that Claudia was describing do have these things. And then we'll discuss a few more things. I'll give you some examples, likely tomorrow on this. And then we can have that one where we replace this thing with this also a derivative that is of the order of the principal part, if you want the highest derivatives that you have. Again, your mathematician friend will tell you, you're on your own. We don't have a theory for you. Good luck. And okay, then you do all sorts of crazy things that physicists we tend to do just to say, well, let's try and find the solution. Whether it's sensible or not, that's a different question, and we're going to discuss that as we go along. Let me say one more thing, again, which we're connecting very slowly, but quickly we're going to get there, to the type of things you could do in general relativity. In general relativity, we first start with an equation that is covariant. So we have, say, GAB equal TAB. Of course, this constant, I just set it to 1. We don't have any sense of time there. So you're going to have to somehow introduce a way to recast this equation in evolutionary terms. This is what I think John Wheeler coined the terminology geometrodynamics. We want to endow or have a way to say, well, the state of our space-time is this much. This is how we're measuring distances here. However, we're going to do it at a later time, provided we have some perturbation of the system. So we're going to have to introduce that notion. As just a little bit of the kind of things we're going to have to deal with, or we'll have freedom to choose. Let me go back to this one. So this flat space-time in one dimension. If we choose standard, quote-unquote, TX coordinates, this is our line element. What we're implicitly doing when we do that is we say, well, we have a series of slices that are at a constant time. Time is advancing to the future. And say the equation of the wave equation is this one. And if I ask what's the solution at a point, well, I have to see its Pi's domain of dependence meet some previous hypersurface. For instance, this one, I account for that piece of data there. And then we know that the causal domain of dependence of this, or the causal domain of dependence of this point is this one. And if I know data here, then I can uniquely specify the solution at that point. And we worked, for instance, reducing this to first order, and we discussed many aspects of that type of equations and how we face them. But we can say, well, let's introduce a new coordinate u, which is t plus minus x. That's our choice. Depending on that, we're going to pick a sign. But now our line element goes from here into that. If we then ask what's the wave equation in these coordinates, is given by this. So it's twice the time-space derivative equal to twice the space derivative. Again, we can say, well, we got a good sense or handle if we try and reduce this to first order equations. let me introduce a variable f in this case, which is the gradient, the spatial gradient of phi. And if I do that, then I can rewrite this equation in this way. And then I see 2 f comma t equal f comma x. Okay, this we could write it, just send the 2 to the other side. And this is an equation that we know. It's an equation that, it's the advection equation, where the speed is a half. Here we are discussed that the eigenvalues will be equal to plus minus 1, and then we say, okay, we know that the speed of propagation in this context is were plus or minus 1, but the moment we wrote it this way, well, first we're seeing a speed that is a half. This just tells us that depending on the coordinates that we choose, just because we're labeling things now with respect to null surfaces, the local speed that we'll measure will change with respect to those coordinates. That's an obvious statement, but it will play a significant role in the context of trying to do numerical relativity simulations, because it's a freedom that we can use to our advantage, or we can really mess it up. The other thing is, if I take a point here, let's say, and I want to know what's the solution at that point, and I look at its path domain of dependence, I see a problem. In principle, unless I cap it somehow, it's not well defined. This is an empty set. So I need to cut it somehow, maybe by putting a boundary here, in which case, say, this is the domain of dependence of that point, or maybe I cap it with another slice that goes this way or this way. So I need to find a way to have a compact domain of dependence. So be it, we'll discuss a little bit about this. These type of formulations is typically what you'll find if you look for ADS-CFT applications. For practical reasons, which we'll discuss later, this is very convenient in that context, this kind of approach. And when I mentioned in the first lecture, the reviews by Chesler and Jaffe, they actively use this. And it's a bit funny that if you ask people working in ADS-CFT about numerical relativity, will tell you, well, the generic formulation is this formulation. If you ask people working in astrophysical applications of numerical relativity, will tell you the generic formulation is that one. And it's just a disconnect of the typical problems that one camp versus the other are trying to solve. But the other point to make is that the equation of motion, that's the equation of motion for F. The equation of motion for phi is this one now. And this one doesn't have a time derivative. It's just a derivative along one of these hypersurfaces. So imagine I cap it off. So I'm doing this. F is something, so perturbations of F move with a speed a half to the left. So this is how F is going to be going. But phi is something that moves here, and it's essentially instantaneously because it's an iteration along that hypersurface. And again, that's intuitively correct. We knew here things move at the speed of light, and we have chosen one of our surfaces to be exactly that tangent to what a light signal would be, and so that's what this is saying. Okay, along that hypersurface, the value of the function is just that simple integral. Of course, you can do this twice with plus and minus, and then your line element becomes proportional to just du dv. This is, if you find it, most often than not, this type of approach is used in cosmology, and you can see why. If you're in cosmology, you're looking back in the past, and it's very natural to just use something that looks like that as far as your foliation is concerned. You just are here, looking backwards to the past, maybe meeting some initial hypersurface, and that's how you're trying to predict the evolution of what an observer would see in the cosmological context. The equation of motion now is this way. Again, if you insist of trying to write it in its first order form, then you function, let's say F is the gradient with respect to one direction. And now the equation of motion with respect to F and phi is, well, the gradient with respect to u is 0 of F, and the gradient of V of the phi field is F. And so you can iterate both of them. And they're just telling you that the solution is just a superposition of something that only depends on u plus something that only depends on V. Okay, so with that, we're going to now dive into numerical relativity. I'll say a few more things. If you were trying to write a code in the late 90s, you had to deal with a whole bunch of things on your own. Luckily, today, there are a number of packages that are very useful. Of course, as any package, you better know what's inside. And all these packages have some advantages and some kind of things that you would like them to do better. But by all means, they incorporate a whole bunch of things, and a few more that I'll tell you in a second. So Cactus is a very common package. It has been around for a few decades. They have consistently been funded to have something that is very well documented. And as far as documentation goes, it's likely that it's very arguably the best. That doesn't mean that it's extremely good, but it's the best of all of the packages that I would suggest you might want to take a look. So Cactus is one, GR Chombo is another one, Spectre is another one. This one implements spectral methods. Then there is PAMR, HAD, this one I was involved with. Still is around, but it's already kind of going not being used much because it was developed 20 years ago. Technology changed a whole bunch during that time. Simflaune is something that is replacing that. And then there is the Einstein toolkit that is something that is intimately connected with Cactus, but it has a whole bunch of infrastructure that will let you essentially write your equations formally, say in Mathematica, and by using several facilities, then it basically spits out a piece of code that then you can interface with Cactus, and then you're going where you want. But the main thing that these things are giving you, one way or another, is something we'll have yet to talk about, and then I'll just mention it very briefly, which is AMR, which stands for Adaptive Mesh Refinement. So this is a way, so remember I said, suppose you have a grid, you have chosen it to be that much, and now you're evolving your system, and your system is, because it's nonlinear, you didn't know what the solution was going to be behaving like. If you knew, you wouldn't have solved the problem numerically, very likely. And let's say some feature that was very smooth begins to develop some very sharp feature, which is physical, and you want to deal with it. I'll give you one example in a second. But so then something that was, let's say, resolved by a whole bunch of points becomes resolved by a single point. So you're actually very, very under-resolving the problem. So you went, again, with a circle that was very, very well-defined to now a Swiss flag thing, something that is arguably very far from being the circle. So adaptive mesh refinement is something that continuously kind of monitors the solution, the wavelengths that your solution is mainly supporting, and if it realizes you will require a more refined grid, it will create points on the fly. At the same time, the opposite is true. If your feature was kind of sharp, but it begins to kind of dissipate, it realizes, oh, I'm working too hard. I don't need that many points for something that is smooth, then it drops points away. Implementing these things in general, especially in the context of 3+1, is a royal pain. So these software packages give it to you almost pain-free. There's never something pain-free, but it's largely pain-free. So an example is, again, if you're thinking of two black holes are going around each other, well, you have many scales in the problem. You have first the scales of the black holes. You need to represent them sufficiently accurately for you to be doing a faithful representation of or capturing the physics of that each black hole is sourcing. You also need to put your boundaries very, very far out. LIGO is measuring really, 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 really far from the source. So you need to capture the wavelengths and the wave sources, the wave shape that get to an observer that, say, somewhere here. So here you have scales of order m, and the observer would be hundreds, thousands of m far. So you need to capture all these. And then depending on the source, if you're, instead of black holes, you're saying you're dealing with neutron stars, then further finer scales show up that you have to be able to put all together and run it in the computational resources that you have available to you. The one example where this was extremely fundamental was the example I told you in the first class, Chopik's critical phenomena. He would not have found things if it weren't for adaptive mesh refinement. I told you you had initially, say, a scalar field that was collapsing right at the verge of trying to decide, I'm going to form a black hole or not. And by zooming in onto that critical parameter, what he found is that these poles get thinner and thinner. Structures started developing at a smaller wavelength that was exponentially smaller every time there was a bounce. And the only way to dig it out is to have something that dynamically adjusted the resolution required near the origin to capture the new physics that was developing. And you can go to Chopik's paper on the subject, which is beautifully written, where he's measuring, say, the mass of the black hole with respect to, let's imagine this is the amplitude of that initial pulse. And he found that the mass of the black holes you're finding depended on that critical value at which you were right at the interface between forming a black hole or not, to some parameter, which happens to be universal. Again, this is something that you couldn't have guessed a priori. But he plots this thing, and it's to whatever, 20 significant digits, the ability that he had, or that code had, to go from P to P star. So that the difference between P and P star was ridiculously accurate. And that required 20, of the order of 20 grids that were, in addition, added on the fly, every grid half, with the spacing half the one of its parent, 20 levels all the way to try and analyze what was going in there. Incidentally, that's a code from late 1980s. You can download it today and run it today. He has it available on his webpage. I have never written a code that would last more than 5 years. And his code is pretty cool. Again, it's written in Fortran, which is an old language, but it's still one of the best languages for this type of tasks. Okay, any questions on that? Good. Let's quickly go into some general statements. So first, we're going to assume, though this is for the time being, we're going to move from it later on when we try and discuss our different applications, then we're going to use the approach of a Cauchy formulation of GR. So we're starting with general relativity. We're not going to go yet on beyond GR because of the type of issues as I just mentioned, the type of equations we're going to have to be dealing with. Once we go beyond GR, generically will give us nightmares, either because they don't even have a mathematical name or because they have features that might break the system completely. So we're going to discuss that in the context and where it comes about. So this is a formulation that foliates space-time in space-like hypersurfaces. We could choose the one where you do kind of null hypersurfaces. This is called the characteristic formulation. But one feature of that formulation is that you have chosen slices that go, say, outwards or inwards at the speed of light. That means you're riding null rays. If you're riding null rays, you have to remember focusing is standard, something that can happen. So if I have a little bit of a focusing power, say if I put a neutron star there, what you might find out is that this ray, so this is your boundary, you have a ray, null ray coming from here, another ray coming from there. They go by this thing, and after some time they cross each other. then you have a coordinate singularity. For those kind of reasons, these characteristic formulations is not used intimately to try and resolve two black holes going around each other. You can do one black hole, you can do a whole bunch of things, but if your main problem, and we like it or not, the main problem of numerical relativity nowadays is to try and predict waveforms for LIGO. Okay, LIGO is an amazing, one of the most important things that have happened in physics in a long time. I mean, there is a reason why a lot of the attention in the field is trying to do that. But as I said, in the ADS-CFT, CFT applications, this is arguably the most common formulation that people use. Okay, but let's start here. So we're going to be foliating our spacetime in with space-like hypersurfaces. We're trying to see how we turn this equation into perhaps some evolution equations, which tells us, given the state of the field, the metric, at some time, we want to know how these equations tell us what the state of the field at a different time, of course, at all points, is. Of course, implicitly in this, when we want to do this, we're already saying, oh, we need a notion of time. So this foliation gives us that. So we can have a foliation where this is t plus delta t, etc. So these are space-like hypersurfaces that we're going to use to foliate, and then they are labeled by t. So associated to this, we're going to introduce now a way to start telling apart kind of events on a given slice to events on the following slice. So I can choose, say, this point, and I can give it coordinates t and x. So we can have two natural ways of relating this point or the points on this slice to the points on the next slice. So I can choose to go along the normal. So let's call this vector NA. So NA is -1. But once I get here, this will be t plus delta t. This point does not have to have the same label. So let me call it x prime. We might have associated to an observer this trajectory. So the direction along the normal need not coincide along the direction of the flow of time that we want to assign to it. So we want to just make sure we account for all the freedom we have. So let me write this again. So I'll do a few more things. So if I have this slice and a previous slide, this is my normal direction. This t and t plus dt. So the first thing we can say, well, if I go along the normal and I ask what's the proper time that I traverse going from this slice that it was labeled with t with the next slide that is labeled with delta t, then it might be, so of course there is a relation on how far these two are in coordinate, but the proper time, well, need not be delta t squared, so we're encoding that information in this alpha, which is a function called the lapse function. Now, a normal, and this is something that you've seen today with Malcolm's in particular, you can define, given a vector, you can and a metric, you can define a projection to the surface that is orthogonal to that vector. So I can define the metric or the projection. This is just more than one thing. Consider that quantity. If I dot this with n, this is simply NA, right? Because n contracted with g is just lower in the index. But n contracted with n gives you minus 1 by definition. We have chosen that signature, minus plus plus plus. This is n minus n, which is equal to 0. So this is serves twofold. It's the projection of any vector to that hypersurface. And it also gives us the notion of measurement of distances on any given hypersurfaces. So this is the full metric can be written as this way. I'm already implicitly saying 0 will be along T, and if it lives on the hypersurface, I'm going to label ij. And so let me just write this first and then explain you what these things are. So this is saying on the hypersurface, I want to measure the distance from here to there. It will be given by the intrinsic metric of the hypersurface plus, well, the coordinates here and the coordinates are there, so this will be x prime. If this were x, and they are the same here, then this distance will be given by beta dt. So this is just, it's a way to capture the freedom we have to label things on the new hypersurface in any way we want. So alpha told us about the freedom that there is with respect to the proper distance between one slice and another one, which differ by delta t in our labeling of the surface. And then this beta is the labeling freedom that we have of points on the next hypersurface. And this beta is called the shift vector. There's one more quantity that we can introduce, which is called the extrinsic curvature. Which is defined this way. So I take the derivative of my vector n. So I want to know, so imagine a flat sheet with a normal and a curved sheet with a normal. Let's say something like that. So if I have a perfectly flat sheet, the derivative of this n will give 0 in this particular case, let's say. But in this one, well, it changes as I go on that curved sheet. So this thing is a quantity that is allowing us to describe how my foliation, how each slide of my foliation that has intrinsic metric gamma ij is embedded in the space-time in which it lives, which is one higher dimension. So our fundamental fields to try and achieve this geometric dynamics of interpretation will be Kij, will be gamma ij, and will be alpha and beta I. So we have, this is a symmetric 3x3 matrix, so it's that one. So we have 6 pieces of information here, 6 pieces of information there, and then 4 more in here. Oh, sorry. My H is my gamma. This is like my pi and my whatever was it, G. My apologies. Thank you. So that says take the covariant derivative of your normal and then project it onto the hypersurface. So that's what tells us the intrinsic metric and how it's embedded, how that foliation is embedded in the higher dimensional spacetime. So now we can come back here. Again, I'm not going to go into all the details. I'm going to give you the main details. Everything else is everywhere. In particular in the notes by Sebastiano, but in the books I mentioned the very first class as well. So out of these, we can do several projections. So I can consider, let's for the moment think of, well, I'm going to keep it. When I was thinking, focusing on vacuum, but let's keep it for now. So out of these, I can say, well, what's the projection of GAB along the normal. So I'm just hitting this tensor with two vectors n. So this is giving us what's the component of this tensor along n. I can also, and this is, of course, the Riemann is a symmetric tensor, so it doesn't matter the next line. I can do the following. So this is, sorry. So this is saying, take one of the legs of the tensor, project it along n, but take the R1 and project it orthogonal to n. So we're decomposing something along this direction, and the another one that lives here. And the last one we can do that, of course, for completeness, is the following, which is projecting the Einstein tensor, both indices, completely onto the hypersurfaces. So this, if you want, is a scalar quantity, has no free index. This is a tensor, this is a vector quantity, which has an index that only lives, so I could have put here an I, only lives on the hypersurface. Or another one where we have the indices both. This is a tensor that lives on the hypersurface. Okay, so what are these things? These different components or these different contractions have names. Out of these, this is a so-called Hamiltonian constraint, which we'll discuss in a bit. Out of this is called the momentum constraint. And out of this is the evolution equation. So I'll say a few more things in a bit, but why are these called this way? It's for the following. Once we express what this thing is, what we're not see, these equations turn out to be an evolution equation for our K, which we can write as an evolution equation for gamma. So this hidden in it is telling us the second time derivatives of our gamma obeys some particular rule. On the other hand, these two involve at most one derivative. And so then this is why they are constraints. We can evolve the gamma ij's as quote unquote for now wave equations on gamma, provided we know we have specified alpha and beta. These are four quantities, one scalar and one vector, so three quantities here, one here. That's four. We know we have four coordinate freedom at our disposal. So we somehow choose those. Then we have everything because we have alpha and beta that allow us to relate this slice to the next slice and these labels in each. And the R1 is an evolution equation given by second order, almost wave equation operator to tell us, given that the state of our field, our intrinsic metric in this hypersurface is gamma, this is what's going to be at a later time. Is this clear? So this formulation is referred to as the ADM formulation, but I caution you with one caveat that what people in numerical relativity call ADM formulation is not the same thing as what people in quantum gravity applications call the ADM formulations. There is a very simple relation between the extrinsic curvature, which has something very geometrical, to what the ADM formulation in quantum gravity is, which usually are called pi ij, and there's just a very simple, you can go from one to the R1 very easily. This one is geometrical. The R1 has to do with the Hamiltonian counterpart of the gamma ij when you write it in Hamiltonian form. It's just a very minor thing. Okay, so one more thing here. So let me erase this one because we don't need. One side observation. And this is an exercise. I suggest you try it. So what we have done here is take the Einstein tensor and then write it in terms of this combination. So what we can do is just rewrite it again. GAB, I can write it as, let me use this terminology here, H, PI, and this one, I don't know, EIJ. So I can rewrite it as H, NA and B, minus pi I. Well, I'm going to use a little bit notation, abuse a little bit of notation, minus PB. So just by using these definitions, you can see that you can rewrite the tensor in that way. And this is an obvious observation. So just if I take GAB and I dot it with two ends, so this will stay alive. When I dot with, say, NA, this one, I get a 0 because P lives on the hypersurface and is orthogonal to each. When I dot this one with NB, this one is 0. And when I dot it either one, this one gives 0. So this is another way of writing the Einstein tensor. We know through Bianchi identities, and this is something that we're going to come back again and again, this should be 0. So you can use this. I suggest you do the following. Put this in here. So use that expression in here. And then that would be a quantity that has a free index, HP. This thing it's a tensorial index P. So you can choose to say, what is the following? Or the following. I'm going to change to H anytime for sure. Those two contributions. And then you can ask the question, what happens if in a given slice, I manage to set my conditions for the constraints to be equal to 0. And then I choose to enforce this equation. What happens with H and P? So what I promise you'll get is an equation of motion that pretty much tells you the following. That the evolution or the derivative of this hypersurface onto the next one, say going along the normal, of what you call the Hamiltonian, that H, will be given by things that are either given by E or proportional to P and H. So if P and H are 0 initially, these contributions go to 0. And if you enforce those E, the evolution equations, then this tells you that you will preserve the constraint. From going from here to there, the constraints will satisfy. And the same goes through for NA grad A of, say, PB. You're going to get the same thing. So Bianchi identities tell you at the analytical level that if you only choose to enforce this one and you set things with the R2 at a given hypersurface, then you will be preserved within the causal domain of dependence, etc. These are things I'm going to get to later on when we talk more about boundaries. But so that's the gist of it. So the basic information is that even though you have evolution equations for, say, the gamma, the second derivatives, and these are conditions that you would seem that you need to impose, they will be preserved if they are imposed in a given hypersurface. Just to give you an analogy, the same happens with electromagnetism. You can have an evolution equation for the electric field and the magnetic field you have constraints. For instance, the no monopole constraint, divergence of B equal to 0. If you satisfy that at an initial hypersurface, and you evolve E and B with the standard Maxwell's equations, and then you ask what happens with the divergence of B, then it's preserved to be 0. So any questions on that? No? Okay. So this is where I give you the bad news. These equations have roughly this structure. Again, I'm not going to be very specific, but let me give you essentially what they are. And then we're going to work to try and fix it. So this equation essentially tell you that the lead derivative along the normal direction of Kij, which you can relate as dt of Kij minus the lead derivative along the vector B of Kij, is given by, roughly, this D is a derivative, is covariant derivative associated with the metric gamma ij. So this D acting on gamma is 0. So it's a derivative on the hypersurface, on any given hypersurface. So the time derivative of gamma, the kappa of K, of the extrinsic curvature, this is some space derivative on the hypersurface, is given by the second derivative of this lapse function plus this kind of combination. Again, I'm being fast and loose on this because we're not going to be dealing that much with that. The main thing is here. And then, by definition, this is also true. So K, the extrinsic curvature, is related to the time derivative of the intrinsic metric. And the time derivative of the K is given by that. So roughly what we have is that the second time derivative of gamma ij is given by, and remember, we worked really hard the first two lectures saying the only thing we need to care is the highest derivatives. If we're in that regime and nature is nice to us, we can ignore everything else. Let's keep going in that direction. So I go and say, okay, this is second derivative. So this is, I'll have to keep it. And the second derivative, so here is kappa. So this is like kappa square, things of the sort. But this here, K. K only has first derivatives. So K square only has first derivatives. We could ignore them. So let's try and ignore them. But the second derivatives are hidden in here. This is a Ricci tensor associated to the metric gamma. So they're here. Okay, we say, well, alpha, I told you, was a free function, was a lapse function that we're going to have to choose it somehow. We're going to have to be smart because there are going to be issues that we better do well with that alpha, and I'll tell you a little bit in a second, but before that, I want to look at the R. So what is the R? We said we know that a Riemann tensor has second derivatives, but let's just dig it a little bit more. So using the so-called the Donder form, and I'm not sure if this is a capital D, so sorry for my bad. I'm going to use purposely Greek letters here because this is true regardless of the dimension we're at. So the Donder form or alpha beta goes like, well, there's a sign, I don't care about that sign, but let me call it this way. G is whatever metric of that space-time, CD, dc, d of G alpha beta, plus the covariant derivative associated to that metric of the trace of the Christoffel symbol associated to that metric, plus lower order terms. So here we have things that have derivatives squared, so we can have gammas times gamma, so we can have dg's times dg's, but we're after the main derivative, the highest derivatives, and the higher derivatives are present here. Here I have second derivative of my metric, and here I have derivatives of my Christoffel symbol. We know the Christoffel symbol has first derivatives, so I have second derivatives here. And here is where we see the problem. What we have in the left-hand side is just a second time derivative of our metric. Let's imagine that we somehow chose a nice lapse function. This is not dynamical. Let's say if I even choose it at constant equal to 1, this is gone. But in here, I see I have roughly gamma second derivative space of gamma plus second derivative of gamma based on that. So if we see this piece with that, seems to be very, very close to our wave equation. For fields, like if they were scalar fields, gamma ij. So in fact, I'm being very loose and I have dropped alpha functions. If we put everything together, this will be nothing but precisely gamma AB, dA, dB of gamma CD. That first part, this one with that one. But then we have the extra stuff. And that extra stuff is what breaks the formulation. We end up in a weakly hyperbolic formulation generically. In special cases, you can make a very judicious choice of alpha, which is coupled with the metric, so it's not true that I can just put it as whatever I want. I need to have alpha related, so I need to choose alpha related somehow to the gamma, so that this alpha comes and fights, quote unquote, this crap that is breaking our nice symmetric hyperbolic formulation. So, in general relativity or in numerical relativity nowadays, formulations are typically, that are most often used, are the following. So we'll discuss a little bit more about this. Generalized harmonic, PSSN, and I'm going to call it CEICO-FZU. Let me just, these are just names. So the first thing, so what is the generalized harmonic thing doing? Well, first let me just backtrack a little bit. We worked really hard to have this geometrical interpretation, but let's look at this one. So if we're in vacuum, Einstein's equations are RAB equal to 0. And if I do RAB for this one, I say, okay, I have this is a symmetric hyperbolic part. I want to get rid of these. These are 4 quantities. So I can try and choose coordinates so that this is 0. So if I choose coordinates, such that the trace of the Christoffel symbol is equal to 0, then I'm golden. And okay, I'm not golden. The one who was golden was Choquet-Broad. Yvon Choquet-Broad in the mid-50s proved local wave posedness of Einstein's equations using this approach. She said, okay, I know mathematics, because she does know a heck of a lot of mathematics. I know that this is breaking my nice properties. I can get rid of it by a choice of coordinates. Short paper, good. That's that. So generalized harmonic say, well, I didn't want to, this is harmonic. If you don't want to give up completely your freedom, because you might not want to choose that the trace of the Christoffel symbols is equal to 0, but somehow you know you want it to be some FA, so something that you want to give by hand under some judicious choice. And if you do that, then you can generalize that, because if this is a God-given, or you give it, and if you have a large ego, you say these are the same things. The F, if you know how to give them for free, come from above, then this is not linked to gamma, or to G, is whatever you gave. So then still your principal part is this one, this becomes a source function, and you're good. And so this is what the generalized harmonic has crucial in it. 2 more minutes and I'll be done. So the BSSN, instead of attacking it at this level, tries to attack it here. But it does the same thing. It says, oh, My offending piece came from derivatives, let's say, of the Christoffels. So the first thing I'm going to do is I'm going to promote them to new variables and give them some prescription so that I can use that prescription to ensure that this guy also evolves in a nice manner. So that's, again, one of the key ingredients of the BSSN. CCZ4 is in some sense a combination of these two, and we'll discuss a little bit. But the other key thing that this and that have is another piece, which relates to the exercise I gave you. The exercise I gave you, which was to use Bianchi's identities to prove that this would be true. I told you that if you do that, then you end up with an equation that goes of the form, let's say for the Hamiltonian constraint, goes proportional to H and PA plus the evolution equations. And we'll look at it more tomorrow in geometrical terms or in abstract terms. Is to say, well, wait a minute, these are my Einstein equations, but I can say these would also be my Einstein equations, RAB equal to something that is proportional to the constraints. Because if we satisfy the constraints would be 0. We haven't changed the equation. But the observation is what happens if we violate the constraints ever so slightly, just because numerical evolution will tell us the constraints are not exactly 0, are slightly often 0. Can we use this to our advantage so that if we are violating the constraints, we try to bring it back to the constraint surface? So pictorially, if your evolution along the constraint is like so, if you start satisfying the constraint, well, you want to ask the question, if I'm slightly off the constraint surface, I'm not solving Einstein equations. I'm solving something that's close to Einstein equations, but not so quite. I want to see if I can modify my evolution so that this one comes back in. And I promise we'll show this. You can have this so that in the end, this turns out to be something. In addition to that, some control parameter here times H. So you can guarantee it through evolution equations that the Hamiltonian and momentum constraint will be such that they're pushed back on the constraint manifold if you're slightly off to begin with or in the middle. So that was the other crucial ingredient, which controls things because, well, I mean, Einstein equations not satisfying the constraint need not behave nicely. So here you're saying, I'm going to force it to do that way. And this is something that generically you can do. You can do the same thing with Maxwell's equations. Every time you have a constraint, you can enforce this in a particular way. So we're going to stop here, but I promise tomorrow we're going to go a little bit more into this. And then I will try to fulfill the promise of saying something about the ADS-FT, something about astrophysics, and something beyond GR. Thank you. Yeah.
So what do you actually mean by solving the Einstein equations without, or when the constraints are not fulfilled? I mean, the constraints are parts of Einstein equations.
Excellent. So, but numerically, you're always going to be making a small truncation error, right? And so then the question is, how would the fact that you begin slightly off would want to work? Of course, implicitly, if you have the nicest possible formulation, you say, if I have infinite resolution, this point gets closer and closer and closer, and eventually making contact with it. But when you start slightly off, you're solving something that is almost Einstein equations with a small variation. And that small variation need not come back this way, it could go that way, right? So that's what we're trying to say. At the analytical level, at the numerical level, how we can use the analytics to enforce that if I have a slightly off behavior to bring it back. The other thing we have to remember is we have a grid, and this grid is feeding truncation error all the time. At every single step, you're putting into the system something that is not supposed to be there. So the way these things accumulate might be such that it takes you completely off. And this is what, the first successful example of this in 3+1 was that of Franz Pretorius when he did the first collision of black holes. And I can show you, if I can dig out the movie, where turning this off or on made a difference between being able to evolve for 10m versus being able to evolve for the full problem that you care to solve.
Okay, but I mean, the equations that you're solving, if you don't solve the constraints, doesn't look like that, right? It doesn't have RAB equals 0.
Right, okay,
It's
so
something else.
first
for
thing,
spatial
okay, thank you.
vector.
So what you would always want to do is to make sure, so let's take a step back and what the requirements were. So you have an initial hypersurface. On that hypersurface, you want to give consistent data. That consistent data should satisfy the constraint. So you choose your initial configuration satisfying the constraint. This is like in Maxwell, making sure if you have E and B at some given state and you want to go to the future, that it better be that the divergence of B is equal to 0. So you give initial data where divergence of B is equal to 0. Now you evolve to the future. What happens is numerically, the divergence of B is proportional to delta squared. And so now would you stay as close or would you widely behave? And that's what slightly reformulating these equations, this one. So if you were satisfying the constraint, these are 0, you didn't change anything. If you're slightly off, you're solving something that's slightly off, but forcing it such that its own error brings you back to the constraint surface.
Thank you.